So good afternoon to everyone. This is Dr. Nimish Kumar Srivast, Assistant Professor in Kumar Engineering College in the Department of Electronics and Communication Engineering. So in this lecture series of the complex topic related to the digital electronics, we were discussing some important topics. In the last, we have discussed about the counters and sequential counters as well. In the sequential counter, we are basically we are concentrating on how to design that sequential counter. So in this topic, I'm going to consider a memory, basic concept of memory and the programmable logic devices. So we all know why we require a memory in the case of a computer system, because whatever the suppose that any program that we want to run, so we are having some interface that is like if you're talking about the processor, microprocessor 8085. Whenever you are writing a program, you have an assembler that is converting that assembly language into a machine language in the form of codes, and that codes are stored in the form of zeros and bits in the memories. So that means whatever the program that we are trying to run is basically first of all getting stored, converted into a machine language and get stored inside the memory. So that memory is consisting of a set of flip-flops, and these flip-flops are used for storing a bit. So that means this memory consists of various cells, and that cells are going to store the series of zeros and ones. So we are requiring a memory for storing a program as well as for storing a data. We know that we are having two basic different concept for the design of the processor as well as the microcontroller. We are having a Harvard architecture, we are having a Van Neumann model, Van Neumann architectures. There are two different schools contradicting, having ideas, and the concept related to that is how we are going to store the program and how we are going to store the data. We are having two things. First is your program as well as another thing is your data. Program is what? Program is a set of instructions. So whenever we execute a program, one by one the machine or processor going to execute the instructions, and that instructions may also require a further processing on the data. So this is what is happening inside a memory. We can store a program as well as we can store data. Harvard architecture tells that there is a separate storage for a program as well as for a data, whereas a Van Neumann models, a Van Neumann architecture is based upon the concept of a same memory which is used for storing the data as well as which is used for storing a program. Now the thing is that what is a program and what is data? Program, these are the sets of instructions. We all know that a set of instructions is called, or a program is called as a set of instructions, and data is something on which we want to perform the operations. As an example, if suppose everyone is having a mobile phone, so in that mobile phone various apps are there. Suppose that there is a WhatsApp, so that WhatsApp app is called a program, and whatever the message that is stored inside that program, inside that WhatsApp, is called as a data. Similarly, your video player, as an example, VLC media player, it is a program, and whatever the videos that we are running through that application or through that program is called as a data. So this is the point of difference between a program as well as data. There's numerous numbers, endless numbers of examples which can easily differentiate what is program and what is data. So we are basically concentrating on the memory. So a memory is a collection or a collection of a storage cells, and that cells stores a series of zeros and ones. Now the thing is that how we can access that particular locations in which our data is stored. So we need something, and that something is called as an address bus. In a processor, we are having three types of buses. Buses are basically a set of wires that is used for carrying zeros and ones. So as I've said, we are having three buses in a processor. First is your called as a address bus, another is called as a data bus, and the third one is called as the control bus. Whatever the location out of millions and billions and trillions of location, we want to access one location. So how we can access that location? We have to first give the address of that particular location. That's sending an address to a memory and selecting the one memory out of millions of locations. that must be having an address. So that sending of an address is done through a address bus. Once that particular address is selected, memory doesn't know that whether a processor want to read or whether a processor want to write at that particular locations. It needs something which can tell him that whether he have to send the data or whether he have to write the data in that particular location. That something is called as a control. A processor is controlling that whether he want to write it or whether he want to read the contents of that particular memory location. That is something done by a control bus. So once out of the million location a particular location is selected, your memory is waiting whether it have to read it or whether it have to send that data. Now the processor will release a control signal that whether he want to read or whether he want to write. So that is something called by a read bar or a write bar. So active low going to inform the memory that a processor want to write it or a processor want to read it. Now this is address and the control bus. Another bus is called as a data bus. Once the millions out of millions location, one location has been selected and memory understood that a processor want to write at this particular location. So from where that particular data going to come? I mean, processor have to send that data at that particular location to overwrite that location. So processor have to send the data through the data bus. That is something done by a data bus. So we are having these three main buses inside a processor that is controlling the memory, which is having a millions and billions of locations, and that particular location going to store a data. So that location contains a series of zeros and ones. If any particular location contains a series of 8 bits, so that location is called as a location which is having a 1 byte. So that is something information we can grab from this particular memory. So after this, once we understood that, so very quickly we can if anybody want to have a quick recap about, we are having a processor MUPI. I am calling it as a MUPI, a short form, which is also called as a microprocessor. So processor as well as a memory, and also we are having IO devices. I am not going into details about that. I am just describing about how processor can access the memory. So for accessing a memory, processor has to processor needs some kind of a buses or connecting wires which carries a series of zeros and ones. So that's why this is your memory. We are having a memory, and this is your microprocessor. So we are having a address bus. Now address bus is there, as well as we are having a data bus, and we are also having a control bus. So this is let us call it by name C and D and A. So A is your address bus. Now the question is why this is a unidirectional, why not a bidirectional? The answer is that who is sending a location address? Processor, because processor want to access any particular location. Out of the these two modules, which is the controller, processor that control that. Processor is having the ability to execute each instruction one by one. So means that controller is a processor. So obviously that particular direction of address bus is from processor towards the memory. So that's why it is a unidirectional. Now the another is data. Data is bidirectional. Now data can be sent from a processor to a memory, as well as if a processor want to read that data will come from a memory inside the processor. That's why it is a bidirectional. Whereas we are having a third bus, which is also a unidirectional, that is a control bus. So control signal will send from the control bus. So this is your memory. So that is a basic concept how we can differentiate these three buses that is used for accessing any particular location inside the memory. Now, if we are discussing about the memory, the thing is that what are the different kinds of a memory in a what are the different kinds of memory in any subjects? Related, whether you are related to a digital electronics, whether you are concentrating on the computer organization and architecture, or whether you are concentrating on a microprocessor. So basic concept related to all these subjects are same. That means the memory. Now in the memory, we are having broadly two categories, that is your primary memory as well as the secondary memory. So primary memory, we are having memory, primary as well as secondary, primary and secondary, right? So primary memory is also having a two types, that is RAM as well as ROM, and secondary memory is having a various types, floppy disk, hard disk, and your CD and your DVDs, your pen drive. So all these things comes under the secondary memory. So these are the classifications of the primary as well as the secondary memory. Now with this, we are having a two types of primary memory, that is a RAM and ROM. RAM is called as a random access memory, ROM is called as a read-only memory. Now random access memory is something which is non-volatile, means that, sorry, random access memory is a volatile, means that whenever there is a change in the situation, it will going to change as per the situation. For an example, situation means that whenever it is getting a power supply, it will store the information, and the moment the power supply is off, all the information get erased in the case of a RAM. Whereas on the other side, your ROM, which is a non-volatile, means that whenever there is a power, it will store the informations, and also when there is no power, it will going to store the information. That means whatever the information that we are storing inside the ROM is permanent, whereas inside a RAM is temporary. Temporary means it will hold the information till you are supplying the till you are giving the power supply. The moment you switch it off, it will, all the information get erased from the RAM. So this is RAM. And RAM is also categorized into two parts: static RAM, dynamic RAM. And your ROM is of various types, like PROM, programmable read-only memories, as well as EPROM, erasable programmable read-only memory. Also EEPROM, that is electrically erasable programmable read-only memory. So these are the types of ROM, these are the types of RAM. We are not going into details about that. So after this, let us take a thing about the RAM. So this is what we have just discussed about the memory. So in a memory, we are having three buses: address bus, data bus, as well as the read or control bus, read write. So that same thing is going to be shown in this block diagram. That is, we are having a memory, that is a RAM, and in this, if we want to access this RAM, we are having a address line. That if suppose that I am having a K address line, so out of from that K address line, I can have a 2 to the power of a K memory location. That means a location inside the RAM. How this 2 to the power K is coming? Because suppose that if we are having a 1 bit, then with the help of 1 bit, what is the maximum possible combination? It is 0s or 1. With the help of 2 bit, what is the maximum possible combination? You can have 0001, 1011. That means there are 4 combinations possible with the help of 2 bits. With the help of 4 bits, you are having 2 to the power 6 to the power 4, that is 16 combinations. So with the help of K address line, you have 2 to the power K memory location inside this memory. So that is something shown in this block also. We are having K address lines. With the help of this K address line, if suppose I am writing, if I have written something on this address line in the form of series of zeros and ones, that particular series of zeros and ones going to locate that particular locations. Now after that, whatever the information that is stored inside that location, that will be transferred with the help of this data line. Now we are having two control signals, read as well as the write. Now this read is something which is signal which is given from the processor to a memory. If processor want to take something from the memory, it is called as a read. If processor want to give something to a memory, it is called as a write. That is the read and write. Now similarly, as this is coming from a processor, that's why this is a unidirectional, and this is moving outside the data, or data is moving outside the RAM. So that's why this is arrow is indicated. Now after this we are having ROM, that means read only memory. So read only memory is a non-volatile memory. Now here in this we are having N inputs and M outputs. Now this N inputs are not the lines that is used for inputting the data, because we know that we cannot write, that writing facility is not available with the ROM. It is only the reading facility which is available with the ROM. So that's why there is no this line, don't just get confused that this is used for inputting the data. This N inputs is basically used to send the address. So this is address, for address, sending the address of a location that you want to access, is something given by this N input line. And out of that 2 to the power N locations, that particular location will be selected, whose values that we are giving inside from with the help of this N input lines, and with the help of N output lines, that particular data which is inside that particular location which we have accessed, going to move out from this output line. So that is the something block diagram for this read only memory. So in this case, as you can imagine, that there is no facility of writing. In the earlier case we are having a read as well as the write, but in this case we are not having any writing facility. You can only read it. Whatever the data is stored in the burned inside the particular chip, going to be accessed by the programmer or accessed by a processor. Now after this, the moment we have discussed this read only memory, now as this read only memory is something which is called as a hardwired, whatever the things that once written, you cannot change that. I'm not talking about its various types like PROM, EPROM, and we are just concentrating on the basic, very basic ROM, that is read only memory. So out of that, as it is hardwired, so if you want to do some changes, you have to completely remove that particular circuitry and add some new circuitry in its place with the desired features which you want that. So it leads to an increase in the cost. So somehow if you are having this facility of programming that particular location, so that is called as a programmable logic devices. So we are having a programmable logic devices also, programmable logic devices, and this programmable logic devices is of various types. We are only going to concentrate on PROM, PAL as well as the PLA. We are not concentrating on the FPGAs as well as the CPLDs, that is the complex programmable logic devices, as well as the field programmable gate arrays. We are not going to into details about that. We are only going to concentrate on the PROM, programmable array logic, as well as the programmable logic array. So we are having, although we are having 5 types, but I am only writing those types which we are going to concentrate. First is your PROM, that is a programmable read only memory. Then we are having a PAL as well as we are having a PLA. So this is a programmable read only memory, programmable read only memory, This is programmable array logic, PAL, programmable array logic, and we are having a PLA which is called as a programmable logic array, programmable logic array. So these are the different types of PLDs, these three basic devices that we are going to discuss. Although you can categorize two more parts, which is FPGAs and CPLDs, but we are not going to concentrate on that. Whatever the things which is inside your syllabus, we are going to basically concentrate only those portions. Now, so before moving into details about this, let us have a quick overview about the arrays of and OR gates that which is used inside these programmable logic devices, and how you can remember, so that in your exam there is no point of a confusion that whether PAL is having a fixed type of OR or PLA is having a fixed type of a AND. So we will discuss that trick also. So let us quickly take the overview of that concept. So we are having two gates that we are going to use it. We are having AND gate array, we are having AND gate array, and we are having a OR gate array, OR gate array, OR gate array, right? And what are the memories that we have considered till now? ROM, read only memory. We are having PROM, programmable read only memory. We are having PAL, programmable array logic. We are having PLA, that is a programmable logic array. Now you can have this trick about the this concept, like with the help of 2 bits, what is the combinations are 4. Let us quickly write that combination: 0 0 0 1 1 0 and 1 1, right? So in this case, the trick is, whatever things that is given by 0, assume it as a fixed, and whatever the thing that is given by a 1, assume it as a programmable. So this is fixed, we are assuming 0 as fixed and 1 as programmable, right? So that means in the case of a ROM, your both AND gate as well as OR gate are fixed. In the case of PROM, your AND gate is fixed, but OR gate is programmable. In the programmable array logic, you are having an AND gate which is programmable, but OR gate which is fixed. Similarly, on the PLA side, as you can see that both are having a 1 1. So that means that both AND and OR gate are programmable. So that is the trick you can adopt in order to remember, like whether we have to make AND gate as a programmable or we have to make OR gate as a programmable in PLA, PAL and PROM or a ROM. So this is a trick one can remember. So now once we got the trick about this different types of PLDs along with the ROM, let us quickly draw the block diagram, because sometimes in an exam you can get this question about describe the PROM, describe the PLA or describe the PAL. So you have to first start your definition with the help of a block diagram. That is very it's very attractive for the examiner to view or to just check that copy which is involving maximum number of diagrams. So there is a very high scope that you will get high marks if you're having if you are supporting your answer with the help of block diagram or with the help of some circuit diagram. That is very beneficial. Now let us quickly take that overview of your ROM, PROM with the help of block diagram. So as we have discussed, you can also, it's the same thing which we have discussed in the previous slide. We are just writing those in terms of block diagram. So in the case of a ROM, we are having AND gate as well as we are having OR gate. So we are having inputs. This is your input and inputs, inputs, and we are having outputs, right? And in this we are having this block diagram, and in that block diagram we have to write whether that particular thing is programmable or fixed. So here we are having both AND gate as well as OR gate as fixed. That means AND gate is fixed, or you can also write AND gate array. Here OR gate array is also fixed. So that is the block diagram for ROM. Similarly, you can draw the block diagram for the PROM. Also, one can draw the diagram for the PLA or a PL, and finally PLA. Same thing. Now, so we are having AND gate. So we'll quickly fill all these things: AND gate, OR gate. Similarly, we are having on this side also AND gate, OR gate. So why we are writing AND gate and OR gate? The trick is if you are just concentrating on the sum of product form. So in that sum of product form, first of all, what we have to concentrate on the product term, whichever we are getting with the help of K-map. After that, summing all those things, then we will get the reduced expression. So that concept is used here also, OR gate. So in the case of PLA, with the help of that previous trick, it is programmable, and this is also programmable. On this side, PLA AND gate is programmable, whereas OR gate is fixed. This is fixed. For the case of PROM, this is fixed and your OR gate is programmable. So this is the block diagram for the complete ROM, PROM, PL and PLA. This block diagram we have written from the previous version of the slide, that this one, how you can remember this thing. Just remember the sequence. Before PROM we are having a ROM, because ROM is fixed. You cannot erase something, or you cannot write something inside the ROM. Whatever the thing is there is permanent, fixed, and that's why we have written the basic form of the ROM, that is ROM. Then we are having PROM. After that, PAL and PLA. Just I have this trick of that both this PAL and PLA would sound like the same thing. That's programmable array logic, programmable logic array. Which one is a fixed, which one is off? Just concentrate on the PL and PLA, which is having in which we are getting the A first. Like this P is there, and after this we are having A in the case of PAL. So write this first and then write the PLA. And after this you are having gates, OR gates, AND gates. Just write the combination 0, 0, 0, 1, 1, 0 and 1, 1. And this is all the block diagram of the ROM, PROM, PAL and PLA. Now after this, the thing is that how we can use this PROM to design the memory. So let us take the example. We want to design a combinational circuit using a ROM, and the trick for that the part of this question is the circuit accepts a 3-bit binary number and output a binary number equals to the square of the input number. So this is the question that is provided to us, and out of these questions, the thing is that it is a 3-bit. At the input we are having a 3 bits, so definitely with the help of 3 bits we can generate a 2 to the power 3, that means 8 combinations, and that 8 combinations, that means output, we are getting output equal to the square of input number. So let us see this concept. So we will write that 3-bit inputs. So 3 bits inputs are A2, A1, A0. So we are just writing the truth table. Basically we are having input and we are having output, and from this output we are also having the decimal equivalent of that output, decimal equivalent of output, and on this side we are writing decimal equivalent of input, decimal equivalent of input. So we are having this truth table that we are going to draw. Fine. So this side we are having outputs. So first of all, let's write the input combination. We are having a 3-bit number, so it will move from 0 0 0 to 0 0 or to 1 1 1, 1 0 0 1 1, 1 0 0 0 1, 1 1 0, and finally 1 1 1. So this is all the combinations, input combinations. So out of this, the decimal equivalent is 0 1 2 3 4 5 6 and 7. So we are having these decimal equivalent of the input, and after this, as per the logic provided to us, we have to write the output. So output we are considering in this, we are having 0, so square of 0 will be a 0. So let us write the square here. 0, 1 it is 1, 2 it will be 4, for 3 it will be 9, for 4 it will be 16, for 5 25, for 6 36, for 7 it will be 49. So we have written the decimal equivalent, whose binary equivalent we have to write it in this part. So let us write this zeros. So here we are having, from this 3-bit we can have 7 out or 8 outputs. So we will write it from B7, B6, B5, B4, B3, B2, B1 and B0. We are having these combinations. So out of this we have to draw this, write the equivalent part. So in this we can write the 0 0 0 0 0 0 and 0. For 1 it will be 0, for 4 it will be 0 0 0 0 0 1 0 0. Right. Now for 4 it will be, then we are having 9, so it will be 0 0 0 0 1 0 0 1. For 16 0 0 0 1 0 0 0 0. For 25 it will be 0, 0, 0. This 16, 16 plus 9, that is 25, right? And then we are having 36, so it will be at 5 to the power 5, it will be 32, 32, and then 7, it will become 0, 0, 1, 1, 1. It will become 37. Then after that we are having 49. So in this case you have already generated 32, and from 32 we are having 49, so it can be 48, 16 if we are generating, and then it can be 1. So this is the 49, that means a decimal equivalent or a binary equivalent of the 49. So in this way we have generated the this outputs for this input combinations. So out of this we have to draw or implement this particular logic gate or this particular circuit with the help of a ROM. So in that ROM, what we have to write, first of all, it consists of a decoder as well as it is having the OR gates. So let us try to implement it first. So before implementing, let us try to get the values for the B0, B1, B2, B3, B4, B5. On the other sides we are having B6 and B7. So instead of using B6 and B7, we can also have B0 to B5, right? Fine. So in this, with the help of that, we can generate all the possible outputs. So now let us first try to write the B0. B0 is, if you closely observe that B0, you can get the B0 from the A0, because B0 is following the A0. You can see that it is a sequence of 0, 1, 0, 1, 0, 1, something like that. On this side we are having 32, and b to the power 5 is 32. 32 plus of 4 going to give 36. So there is a little mistake here. So it should be 4, because 32 plus 4, it will be 6, this one, right? So we can see that B0 is exactly same as A0. So we can write B0 equals to A0. Similarly for B1, it is entire 0. That means B1 will be 0. We can ground that particular terminal. And here it is B2. Let us try to write the minterm for this B2. So B2, for minterm we know that we have to concentrate on the combination for which we are getting 1. So we are getting 1 for B2 on the 2 as well as on 6. So 2 and 6. 2 and 6. For the case of B3 is giving 1 at 3 at 5. That means it is giving 1 at 3 and 5. Now B4 and B5. B4, we are having B4 at 1 at 4, 5 and 7. 4, 5 and 7. 4, 5 and 7. Similarly, B5 is giving 1 at 6 and 7. So B5 giving 1 at 6 and 7. Right? So in this way, we can get we can realize this circuit with the help of PROM. First, try to write the truth table. After that, once you have written the truth table, next thing is that you have to implement it or get the reduced form with the help of KMap, right? So we can get the minterms. So based upon the minterms, we can write or we can implement this circuit by using a ROM. So next part is that we have to draw the circuitry. So let us try to implement it by using a ROM. So as we are having 3 inputs, so from this 3 inputs we can get 8 locations. Right. So this is your A0, A1 and A2. Now let us try to write the, first of all write the values that we have used. We know that B0 equals to A0, B1 equals to 0, B2 equals to 2 and 6, 2, 6, B3 equals to 3, 5, 3, 5, B4 equals to 4, 5, 7, 4, 5, 7, B5 equals to 6, 7, right? B5 equals to 6 and 7. Now, so these are the min terms that we got. Now, based upon this min terms, we can get the output. So here it is your B0, B1, B2, B3, B4, B5, B6 and B7, right? So we are getting these outputs. Although you are getting these outputs, but with the help of only 6 outputs, you can realize this circuitry. So there is no need to take this B6 and B7 line in order to implement it by using the ROM. So let us first implement it. B0 is continuously attached with the A0. So we can implement it. B0 is continuously attached with the A0. So this is your A0, right? So it is continuously attached with the A0. So we can have this, and this is your B0. This is your B0. Similarly, we are having B1, which is continuously attached with the 0. That means it is grounded. So B1 is continuously grounded. That means logic 0. That means logic 0. And we are having B2, which is having 2 and 6 as a min terms. So 2 and 6 as a min terms. So we will draw the OR gates. So the concept is that the number of OR gate depends upon the number of outputs. So if you are taking this B6 and B7 also as an output, so what is the number of OR gate that you will require? It will be from that means 8 OR gate will be required, but that OR gate will be continuously attached with the B6 and B7, which is having a 0, which is grounded. So there is no need of just inputting, there is no need of taking OR gate and give all its input as a 0. What is the purpose of that? Instead of that, just remove that. So we can remove this, B6 and B7, right? So although if you have included, it's not going to put any matter, it's just increase the cost. So after this, we are having a B2, right? We're having a B2 which is giving you a, so instead of that we can write here as D0 to D7, D6, D5, D4, D3, D2 and D1. So we are having, we will use OR gates B3 and we will use B4. Similarly, we will use B5. Now this is B2 is attached with the 2 and 6, so that 2 and it's attached with this one, and the B3 is attached with 3 and 5, attached with 3 and 5. B4 is attached with 4, 5, 6, 4, 5 and 6. Similarly, B5 is attached with 6 and 7, so it will be 6 and 7. Dot is in, it is etched inside the chip. So we can realize ROM, any circuitry with the help of a ROM. In that ROM you will be requiring a decoder, and after that it will be having a fixed OR gates. So that is the detail about the ROM. We have discussed all the types of programmable logic arrays with the help of a block diagram, and this is the one example related to this ROM. So that's all for in this lecture video. So time allows, then we will take one more lecture in order to implement that PAL, PLA and PROM with the help of numericals. So that's all for today. Thank you.